Hi, my name is Mark Rulo. I'm one of the mathematics consultants in the Learning Success Center at Mount Wachusett Community College. In this video, I will explain binomial probability distributions. The important thing to recognize in these distributions is the word binomial. Bi means two, and when you run a trial in a binomial experiment, there are only two possible outcomes, either success or failure, heads or tails, yes or no. For these experiments, the probability of success has to be the same for each trial, and the outcome of one trial will not affect any other trial. For example, if we flip a coin, we get heads or tails. If I happen to flip heads 6 times in a row, what is the probability of getting heads on the next toss? It's still 1 out of 2. The coin doesn't know or care how it was flipped before. If those conditions are met, we can then calculate the probability of x successes out of n trials. There are a few methods for calculating probabilities in a binomial probability experiment. A common method is to use the binomial probability formula, which looks like this. The left side says p of x. It does not mean p times x. It means the probability of x successes, and that equals NCX times the probability of success p raised to the x power times the probability of failure q raised to the n minus x power. NCX is a special function for combinations. It is also sometimes written as NCR. It is used in other problems. For example, the ice cream shop down the street has 6 flavors. If I want to get a 2-scoop cone and pick 2 different flavors of ice cream, how many choices do I have? That depends on if order matters. Does chocolate on vanilla count as a different choice as vanilla on chocolate? If yes, then we are calculating how many permutations are available. There are 30. But if order doesn't matter, then we are talking about combinations, and there are 15 different choices. On most scientific and graphing calculators, the NCR is already built in. On the TI-83 and 84, you enter the big number first, in this case 6, then hit the Math button, arrow over to the PRB, which stands for Probability, menu, arrow down to 3, hit Enter, put in the smaller number, in this case 2, and hit Enter. If you are using a different calculator, you may need to look up how to use its NCR function. In these problems, little p stands for the probability of success, and little q stands for the probability of failure. Since there are only 2 possible outcomes, success or failure, then p plus q equals 1, so q equals 1 minus p. Now we can try an example. What is the probability of flipping a fair coin 10 times and getting heads exactly 3 times? Here, the probability of success is 0.5, and the probability of failure is also 0.5. We have n equals 10 trials, and we want to know the probability of x equals 3 successes, and we can put it in the calculator. Remember to use the caret to do exponents, and if you are actually typing 10 minus 3 for the exponent for q, to put that part in parentheses. The answer to 3 decimal places is 0.117. For certain values of p, you can use a binomial distribution table. There is one at the back of your book, and you can find a copy on the Learning Success Center LibGuide site. Here's what part of the table looks like. Notice the values of p start at 0.01 and then are in multiples of 0.05. We could use the table to get the answer to the question we just posed. Start by finding the part of the table for n equals 10 trials. Find the column for p equals 0.50 and go down until you find x equals 3. There it is, 0.117. For binomial probability questions with values of p that are found in the table, getting the answers will be pretty straightforward. But life's probabilities don't all happen at convenient 0.05 multiples, so you may have to work with a formula. Note, when doing a binomial probability experiment, you must also consider the possibility of 0 successes. For example, a particular surgery has a 0.72 probability of success. What are the possible outcomes if 3 people go for the surgery? Well, there is a calculable probability that all 3 will be successful, but it could end up that only 2 are successful, only 1 is successful, and that none of them are successful. We could make a table that looks like this and calculate the probability for each. If we add the probabilities for all the outcomes, we would get 1.000 unless a digit is lost due to rounding. Because no other outcomes are possible. If 3 people go in for the surgery, there is no way 4 successes could happen. This point becomes important when the number of trials increases. Let's say n equals 10. Then we have these as possible outcomes. Now for example, let's let p equals 0.44, and let's calculate the probability of one of the outcomes. Let's say when x equals 2. P of 2 equals 10c2 times 0.44 raised to the second power times 0.56 raised to the 8th power, and that equals 0.084. What if I'm asked the probability of no more than 2 successes? Then I would have to find p of 1 and p of 0 and add those probabilities to p of 2. That's not so bad. Note, if you see a problem with a 0 in the exponent, do not skip it assuming that the answer will be 0. Remember, any number raised to the 0 power equals 1. Now, what if I want to know the probability of more than 2 successes? One way to solve it would be to make the calculation 8 separate times and add those probabilities together. That's a lot, right? Except, remember, the sum of all these probabilities is 1. So if I want to know the probability of these 8, that would be the same as 1 minus the probability of these 3. Sometimes it's easier to find the probability of the complement and then subtracting that from 1. I hope this all makes sense and you've been able to follow along and understand what to do and what it means, because I think you should be able to make these calculations by hand this way. But I also want to show you a couple of other methods for solving these problems. One is by using Excel. You may have seen the video I made about using Excel for statistics class. Here's another function that may come in handy. First, let me fill in some cells. Here we'll have one for the number of trials, one for the number of successes, and one for the probability of success. To find P of 3, as we did in the last example, I will click a free cell. I will hit equals to indicate that we're going to put in a function, and then start typing Binom. The full name is binom.dist. Double click on it when you see it. It now needs 4 numbers inputted. The first number, which is abbreviated number underscore s, that's the number of successes. So you can click on that cell. Next, it needs to know the number of trials. We'll click on that cell. Third, we need the probability of success. And finally, it asks for cumulative. The cumulative number is either 1 or 0. 1 for yes, 0 for no. A no here means just give me the value of p of 3, and that again is 0.117. But if I do this again and put a 1 for yes in cumulative, it will add all the probabilities for all the values of x that come up to and including 3. That is p of 0 plus p of 1 plus p of 2 plus p of 3, which is 0.172 when rounded to 3 decimal places. Nice, right? If you have a TI-83 or TI-84, you have the same function built in. To get a value for a single value of x, use the Binom Cdf function. To get there, hit the second button, then vars, scroll down to Binom Cdf, and hit enter. In this calculator, you enter the number of trials first, then a comma. Next, enter the probability of success, followed by a comma, then the number of successes you want. You can close the parentheses if you prefer, and enter, and it's 0.118, again, to 3 decimal places. If I want the cumulative probability of p of 0 up to p of 3, I would use the Binom Cdf function. It's the same process. Hit the second button, vars, scroll down to Binom Cdf, hit enter, and then it's 10, 0.5, 3, enter, which gets us 0.172 to 3 decimal places. Easy peasy, mac and cheesy. You may be asked about population parameters for binomial distribution. These are pretty straightforward. The mean equals n times p. The variation equals n times p times q. And the standard deviation is the square root of n times p times q. Some students may see questions about multinomial experiments. And when I first came up upon those in a homework question, I was really confused. I could not find information about that anywhere in the book in chapter 4.2 until I noticed it tucked in amongst the homework questions after that part of the chapter. An example of this problem may look like this. Crossing plants a certain way will result in either tall and colorful, tall and colorless, short and colorful, or short and colorless plants with corresponding probabilities of 9 over 16, 3 over 16, 3 over 16, and 1 over 16. Now, if 10 plants are selected, what is the probability that you get 5 tall and colorful, 2 tall and colorless, 2 short and colorful, and 1 short and colorless plant? Here, there are more than 2 outcomes, hence the multinomial in the name. For a multinomial experiment, use a modified version of the equation for binomial experiments. In this example, it would look like this, which equals 0.033 when rounded to 3 decimal places. And that should cover everything you need to know about binomial distributions. Let us know if there was anything in this video that could be made more clear for a future update, and let us know if there are other videos you would like to see in this series. As always, check out our website for more information about services available in our Learning Success Center, or call, email, or stop by. Good luck, and I hope to see you this semester in the Learning Success Center.